All right, so as we get organized here a little bit, the quiz is over the first three sections in the book. So the appendix problems, for the most part, that's not on the quiz. I mean, yeah, one of the things we did in the appendix was practice writing equations of lines. Well, that is on the quiz when we talked about piecewise functions. So when I say the appendix problems aren't on the quiz, I mean, for the most part, I'm not going to have you. You're not going to work out a bunch of log problems and e to the x problems, that kind of stuff. That's not on there. Or those story problems we had to set up to do, right? But one of the first things we did in section 1 was these piecewise functions, right? Where we had a part of a circle and maybe some lines and so forth. And so we want to be able to do that. I told you that will probably be something you have to do. So, this point slope form here of a line, we have the circle equation. You need to know that circle equation, okay? So if you have a picture, there's a center, there's a radius, you need to be able to do that, solve for y. We'll practice one here in a little bit. I'll just throw one up there and let you try it just for practice. Okay, section 1 is when but that, really, what else do we do in section 1? We just kind of reviewed function notation, input, output, domain range, that kind of stuff. And so that, most of that should be reviewed kind of thing. But you can go back, and I don't really have any review question. I mean, sometimes before a quiz, the book has some review questions. They don't really for this stuff. So you're just looking back over your homework, that kind of thing. If you want to revisit any of the class videos, that are online, that's certainly something you can do too. A lot of it, I said on Friday, a lot of it is stuff in the section 2. Now, I wrote even, odd, periodic. That's when we reviewed those things. So we had a lot of questions about various types of functions, even the stuff in section 3. The homework for today was about all these different types of functions. Now, eventually, we want to be able to memorize those without a calculator, know what the trig graphs look like, know what e to the x looks like, know what log looks like, know what polynomials look like. But that's not really going to be tested on the quiz tomorrow. Okay? You'll get to use your calculator to graph some things if you need to and so forth. So memorizing those is not really necessary for a moment. But quizzes going forward, yeah, we want to begin to be able to do that. But we do want to be able to look at those functions and answer questions about if they're even or odd or periodic, and what does that mean. So like the homework we had there. Now somebody, as we were going through it first or second block, we realized there were some other things I kind of left off this list here. We also had a bunch of terminology like local max min and roots of a function and inflection points. And that's where we talked about concave up and concave down. Right? Know what those things are. So like on today's homework, it said where's the function increasing? Where's it concave up? Those kind of things. So that was in section 2 as well. A lot of that terminology. So you want to be able to answer questions about function that way. And then section 3, like I was saying, section 3 was mostly about introducing you to these different families of functions. And eventually here, in later quizzes, you might be asked some stuff without a calculator where you have to kind of know what those graphs look like. The shifting, I kind of left that off too. Section 1.2, that was 1.2, a big part of that was all that shifting and stretching of those graphs, right? That was a big part of section 1.2. And then that also carried over here into the questions on 3. So we want to be able to discuss those kind of things. But the last thing, and we'll practice this here in a minute. Matter of fact, we'll do it right now. I want you to be able to get on your calculator. I want you to be able to put in a function, set a window, trace, be able to find the max and the min, maybe be able to find the roots, etc. So I want you to be able to do that on your calculator. All right. So everybody get your calculators out right now, and oops. All right, and let's get logged in if you're not already. do that if you forget your Chromebook. Not by me. Somebody the second block was asking me if we're going to use the Chromebooks in here, and I'm pretty boring. I mean, every day it's just kind of like, okay, get your homework out, okay, get your calculators out, get logged in, and now I'm going to have to add to that. Now it's going to be get your homework out, get your calculators out, get logged in, put your Chromebooks away. That's pretty much what we'll do in this class. So that's probably how much we're using Chromebooks. There are some things. There are some websites with some review things, with a couple of different, some practice things that we do for a couple of different tests that we take. Along the way, I'll explain those more when we get closer to them. And there are some good websites with some good practice and stuff. So there are some things out there. Here later in chapter 2, we're going to do some stuff with limits. And there's a cool website with some animation and stuff that's pretty good. So, and I usually put those links on my website and let you do it, but now we could spend a little time in class with Autumn if we want to. So there may be a few things we do. But, all right, let's let this person be the presenter. Neil, you're a presenter. Thank you very much. Okay, so everybody else, let's go into in your calculators, and Neil as well. Let's put this function in. Let's say f of x equals, I'll just make one up here, 70 sine x minus 10 plus 15. I don't know. And let's say I give you this function and I tell you to graph it from zero to 10 on the x, and the y is say negative 60 to 90. So this would be the x, and this would be the y. So I give you a window, I give you the function, and then let's say I also told you that this represented the temperature so many months after January 1. January is month 1. So X would be the month, and this is the average temperature. Okay, maybe the average daily temperature in certain months. X is in months. Okay, so what would this look like? So if we go, now you don't put that in there, I don't think. Does that work, Neil? Have you done? Oh, okay. I think all you do is that right there. Yeah, you put your equation into your F1, hit enter, okay? And now, oh gosh, that's crazy. Looks like a bunch of lines. Well, what you got to do now?
Adjust this window.
Got to go change the window, right? So we go to menu, we go to window, menu. Yeah, there you go. Menu. You can just hit the 4 too. You can just hit the number. That's usually quicker. Hit 4, then 1. Window settings. And so that's where we set our x min and max. So our x is going to go from, what did we say, 0 to what? 10?
10.
So it goes 0 to 10, and you can just hit tab or hit down arrow. And then here, this was what?
Negative 60.
What did I do? Negative 60 to
90.
90. Negative 60 and then 90. So I want everybody to be able to put in a function, be able to set a window, hit enter, or click OK. All right, something like that. So that makes sense. The temperature goes up, in the winter, it's cold or whatever, right? So it might look something like that. And then I want you to be able to trace. So I might ask you some questions about it, like when is the temperature the highest? So we want to trace, right? And so it looks like, so we go to trace and graph trace and puts it right there, is pretty close. So let's just hit the right arrow. Let's just okay. Now it's jumping all around. What are you doing there? You're so with your trackpad, is that what you're doing? Yeah. Okay, which is fine, but and you can do that. The trackpad is not real user friendly, I don't think. Let's use the left and right arrow key real quick here. One thing with trace, it'll screw up your window, as you can see for his. All of a sudden, if you trace outside the window, then it starts jumping around. Hit your left arrow key. Just hit the left arrow key a few times for me, would you? Is that what it's doing? You're just hitting the left arrow one time and it's jumping that much?
Mm-hmm.
What's that? Hit the right arrow just one time for me. Okay, hit it again. Hit it again. So one time it jumped from, you just hit it one time and it jumped from here up to here?
Sometimes it does that, and sometimes it goes smaller.
Oh, interesting. Okay, is everybody's doing that, or? Okay, all right. Okay, and this is good, because one of the things I wanted to do was get everybody in the same settings here. So go ahead and hit menu. Everybody might want to do this. Let's go ahead and hit menu. Go down to number 8, which is settings. And see where his says float 3. Does everybody else say that?
Yeah.
Okay, we want to change that. So let's go to the display digits, and let's change that to just plain old float. Float 3 would be great if you were doing significant figures. If you're doing significant figures and you're only supposed to have 3 sig figs or 2 or 4 or whatever, set it to that, and that's all that will display. And it will keep it around and do everything it needs to and keep it in those sig figs. But we're not doing that. We want to see all the decimals we can. So we want plain old float. Go ahead and hit enter. Now I'm curious. Okay, and then hit OK. All right, and we usually want to just leave it on there. Okay, now you can see how you see more decimal places here. Okay, you should be seeing more than maybe you were before. Okay, which is good because we want to do that. All right, now go into menu again there, Neil, and go to trace, and go to trace step. Okay, what does everybody say there? Yeah, I think that's what we want. So somehow yours got set to 3. Set it to automatic, and that's what was happening. Yours was jumping around by 3s, but it did find the maxes and the zeros. It's kind of set when it's in trace to it'll go by 3s, but if it finds any maxes, local maximums, or any zeros or roots, it'll find them, which is kind of nice. Now hit your left arrow. Okay. See, and now your left arrow, keep going. Now keep hitting your left arrow. Now it's going in smaller increments. See, so it's not jumping around. That's really where I think you want it set most of the time. But it is nice. Go ahead and hit the right arrow now. It is nice that when you get to a max, it will find that for you, kind of automatically. Okay, and you get right. Oh, it should have. Did anybody else's do that?
There's another setting for that.
Huh, now it was doing it for us. Is there another setting for that?
Yeah, it's in the settings.
Okay, go to menu again. Go to menu again. Because we want to make sure everybody will do this, although later on, so go to 8, settings.
It's at the very bottom. You have to scroll down.
Okay, scroll down.
It says automatically find increasing interest.
There you go. Yeah, see, his is checked. Because it should be checked, I would think. It's really interesting. Okay, go ahead and hit enter again. Okay. Okay. Well, let's talk about what you do if it doesn't do that. It's pretty simple to do. So if you're tracing along and it's not finding the maximum, it's not showing in yellow there, it's saying maximum, just go to menu. Okay. Go to menu, go to analyze graph. Choose maximum. Number 3. And it's going to ask for the lower bound. So just hit your left arrow or use your trackpad to get this dotted line to the left of that max. Right there is fine. And hit enter. And then you want to go to the right. You can just arrow to the right or use your trackpad, either one. Yeah, you don't want to go quite that far. Okay, you just want to get just barely right of it. Okay. That's probably good enough. That's probably good enough. You can hit enter now. And it should find, and there's the max. There's the max. Okay? So if you trace and it gets right to there, same thing with zeros. You can, okay, you should trace and it should just find it for you, but if you go menu and analyze graph, you can find maxes, mins, or roots. Okay? Now, so then what question I might ask, what was the hottest it ever got? Well, 85 degrees, right? When did that happen? Well, if this was months, that'd be in the 5th month, which is May, right? If I said to the nearest day, well, it's a little trickier. Then you might take that decimal and times how many months in May? 30 months. How many days in May? 31? So go to the calc, you hit your scratch pad key here, hit your scratch pad key, and go to the calculator part and take 0.28, what was it, 0.287? What was it? 0.28761, 0.28761 times 31. So it'd be about the 8th day of May, right?
I think
Okay.
it's almost the ninth.
Round to the 9th, right? So I can give you some leeway, nearest day, so 8th day, 9th day.
But what
Eat-
time?
Yeah, I didn't get the time, okay? So, right, and so, again, be able to put an equation in, get a graph, be able to set a window, be able to trace along it, be able to answer some questions about it, you know, its inputs, its outputs, what they mean, that kind of thing. Be able to do that, okay? All right, thank you, Neil. So back on this, so those would be some of the things, you know, we want to be ready for. Now, there are going to be some questions, I think, on the homework, and we'll go through those. And then, matter of fact, before we do that, why don't we go ahead and just do that one problem I said we would do for quick review. So I'll let you just in your homework pages there. Let's say you had a circle, you had an equation, you had some piecewise function, and we had part of a circle. It went kind of like this. And right down here was the center, and it was at 4, -2, and we had a radius of 3. So let's say you had a piece of a circle, this piece of a circle, here was the center, here was the radius. Write the equation of that circle and solve it for y, because that's what we would need if we were doing a piecewise function. Right? So go ahead and do that. I'll give you a couple of minutes here. Okay, so I got the first part of the equation, which you just have to know that, right? You're just going to have to know the basic form of a circle equation, and we want to get the y by itself, correct? There's no need to FOIL out this x minus 4. Just leave it as a quantity that you would subtract over to the other side. What's the next step? Square root both sides, plus or minus square root. Now at this point you might decide which one of those you need. Which one? The plus, because it's the top half of the circle. That's not the whole half, but we'll take care of that later. Okay, if it was the bottom half of the circle, we would want the minus. Okay, what do we do with the 2? subtract it. And I talked about that the other day. I usually put that in front just so we don't confuse whether it's underneath the square root or not, but it doesn't matter. You put it behind or in front, whatever. Okay? So we only want the plus. So then the final step would be to take that, and we don't want to include the y equals because that's already in our piecewise function. So we would just write, depending which piece it was, -2 plus square root 9 minus the quantity x minus 4 squared. We just leave it like that. Remember, you can't square root the 9. You can't square root those pieces because you can't do that with a sum. So you just square root the whole thing, just leave it. And then this would go from where to where? We don't know, do we? Let's say that's 1, and let's say that's 5. So we would include 1, and we would not include 5. Right? And that's how we take care of the fact it's not the whole top half. If it was the whole top half, we'd have 3. We went down to 7. Right? It would have went 1 to 7 if it was the whole top half. But okay, just so that was something I had said early on that you're going to have to be able to do. So just be prepared for that, because there are other things you're not going to be able to really study for. There are things that you know about even odd functions, periodic. You know about these things, but you might have to put them together in various ways and some questions. And so you're just going to do the best you can. I know there's one on number 19 I wanted to talk about a little bit that kind of fits that description of what I'm talking about there. But one of these, if there's some of those questions that are a little trickier sometimes, that really make you think, really stretch your understanding of what's going on, you certainly want to take advantage of these questions you know are coming, right? The ones that you know are going to be similar to this, and be ready for those. Okay. Let's go to the homework question. Okay. I do want to talk about 19. Okay. In case you have that one. Anybody else have another one? 49. That whole 47 through 49 section there. Okay. Now on 24, let's see, 24, 26, 31, that section, that would be the kind of thing where you would graph that on your calculator, right? And you might answer some questions about it, like it says domain and range and so forth. All right. Now, these questions, like I told you, you could put them into your calculator and then answer these questions as related. Most of these questions are from section 1 and 2, domain and range, even odd functions, periodic, right? All those things, those ideas are all in sections 1 and 2. So let's look at number 19. Now let's go ahead and get a graph of the tangent up here. So let's see. Let's get another volunteer. I guess you're not really volunteers, are you? Oh, hey. Oh, Alex. Cool. Did that work, whatever you were doing there? Mm-hmm. Oh, is that one? Oh, yeah. Oh, don't. Nobody look at that. Okay. Hurry, make it go up. Oh, no. God, what? That's not your fault. Okay. My February.
Yeah, they already don't know what it is.
All right.
Except for maybe Kevin.
All right. So with tangent, let's put in the tangent graph. Let's put in the tangent graph here. Okay? And now hopefully at some point, tangent x, and let's go to our window, and now on this problem they said 0 to 2 pi, but let's put in -2 pi, or leave that. Just leave that for a second. Let's leave that for a second. So remember, that's what tangent looks like. It's kind of these increasing little S-shaped kind of things, and the asymptotes are where?
Pi plus pi.
Not pi. Pi
halves.
halves, right? And see, I'm recording this, so I'll flip back and forth here. So tangent, remember, is sine over cosine, and the reason it has asymptotes is because of that cosine in the bottom, right? Anywhere cosine has an output of 0, this is going to be undefined. Well, where's cosine 0? Think of the unit circle. Pi halves 3 pi halves, right? That's where cosine is 0. So if pi halves 3 pi, so every pi units, you're going to get an asymptote. So as we go through this problem, what is a natural domain? Well, it's all reals except pi halves plus pi. Now, I'm not going to make you write it this way necessarily, but this would be a good way to write it. You probably did this last year. If n is 1, 2, 3, or -1, -2, -3, this would give you every pi units, right? Both left and right, you would have an asymptote. So x can be anything but that. You could just write that out of words, too. You could say it's all reals except pi halves and integer multiples of pi, or pi halves, 3 pi halves, 5 pi halves, ... And negative pi halves, negative 3 pi halves, ... I mean, you could do that.
So can you not write this as like inclusive and exclusive brackets?
You could do that, too. Now, what would that look like on this one? You know what I mean? If you write, I mean, the problem with that on this one is there's a bunch of them. You know what I mean? What did the back put on this one? Did anybody look it up? Did they write it like this? And kind of a word explanation. I mean, the brackets are kind of hard on this one because it'd be negative pi halves to pi halves. Then it would be, you know, you just have kind of an infinite number of these pi width, you know, things. Exactly. Yeah. Sine, you know, all real. That's like all real. But you know, you could go negative infinity to infinity, those kind of things. Yes. But on this one, it's just a little tricky, right? And so again, I wouldn't worry too much about this notation. That's not going to really be an issue for you tomorrow, for sure. But yeah, it's something you did last year. Something we should be able to do. The range in part B would be all reals, right? Negative infinity to infinity are all reals because if you go back and look at that picture, the y values go on forever, going both ways. Okay? Part C is, this is the one that I really wanted to talk about, part C for sure. Because this would be in that category of questions that are kind of difficult, but it uses information that we have talked about. Okay? Now, I might have given you, if this was on the quiz tomorrow, I probably would have given you this part. Now, I think everybody should know that, but at this point, I might go ahead and give that to you. And say, I might have worded it this way. I might have said, use the fact that tangent is equal to sine over cosine to show that tangent is an odd function. Okay? Now, what's an odd function mean? Origin symmetry, what else? Opposite in, opposite out. Now, the fact that they said use sine and cosine means you would not be able to just look at a graph and say, hey, it has origin symmetry, so it's an odd function. I mean, clearly it has origin symmetry. It is an odd function. But the question said use sine and cosine. Okay? So here's what you would need to do for part C. Remember, opposites in, opposites out looks like this. When you put opposites in, you should get opposites out. That's what opposites in, opposites out mean. So what I would do here is I would take and put an opposite in to the tangent function, which would mean I would put opposites in to the sine and cosine functions here, right? If tangent x is sine over cosine x, then tangent negative x is sine negative x over cosine negative x. All right? And we talked about this now. What kind of function is sine? Odd. So sine negative x could be written as negative sine x. Cosine is an even function. Cosine negative x could be written as cosine x. What's negative sine x over cosine x? Negative tangent x. So therefore, opposites in, opposite out. Tangent x, or tangent negative x is equal to the opposite of tangent x. That makes tangent an odd function. That's what I would be looking for on that one. Now that's pretty tough to be able to put that all together. Put together what we learned about sine and cosine being odd and even. But the notation, if you're good at the notation, you can write it. It's that. Okay? So, you know, that's the kind of stuff that, yeah, look over those properties, but make sure you know more than just odd function means origin symmetry, okay? Or you might remember it means opposites in, opposites out, but what does that really mean? What does opposites in, opposites out really mean? It means this right here, okay? Graphically it means something, but it also means that notationally. So if you need to work a problem using notation, you want to be able to do that. Okay? So that's part C. So that was tricky. D says is it periodic? Yes. What's its period? Pi. So that was easy. Where is F increasing? Well, it's always increasing, except where? Well, it's not increasing where it doesn't exist, right? So at the asymptotes, right? So everywhere, so you could say it's increasing everywhere, because these graphs, remember, we're talking about from left to right. As you go from left to right, this graph is always going up. So it's increasing everywhere, except where it doesn't exist, which is at pi halves. And let's see, between 0 and pi, that'd be what, twice pi halves and 3 pi halves? So you could say it's increasing everywhere, but x equals pi halves and 3 pi halves. Or you could use notation. You could say from 0 to pi halves. From pi halves, I think this is what they said in the back of the book. From pi halves to 3 pi halves, and from 3 pi halves to 2 pi. So this is where it would be increasing. Right? That's the same as saying everywhere but pi halves. Okay? So increasing. Are there any local maximum endpoints? No. Not on this graph because it's always increasing. So that would be no. Does it have, or where is it concave up? Well, that would be right here. Right here. And then we're outside of 2 pi here. I think this is this 2 pi right here? I think that's 2 pi right there. Okay? So it's concave up from 0 to pi halves, and it's concave up from 3 pi halves to 0 to pi halves, it would be concave up, and it would be concave up. What is this? This is pi. Pi to 3 pi halves. That's where it would be concave up. Okay. And then does it have any inflection points? Aren't these inflection points right here? Okay. 0 pi, 2 pi. Now, did they want us to include? They didn't want to include 0 and 2 pi, so actually the only one then would be pi. Yeah. Now on this one, you would include this. I mean, I'm not following. Yeah, this would be okay. But yeah, I might have included. What did I include something on another one? You might be right. On yeah, these would all be okay because it doesn't include the 0, it doesn't include the 2 pi. Yeah. But if we have to give an actual x equals as an answer, like here, so it would be x equals pi. Yeah, because we wouldn't want to include the 0. Okay. So those actual points wouldn't matter. All right. What else? Roots. Any roots? No. Same thing, right? The inflection point is the root, right? Remember, inflection points is what? What's inflection point? Changes concavity. Yeah, changes concavity. So it goes from concave down to concave up. Okay, but those are also the roots. Roots, remember, are zeros. Zeros and roots, same thing. It's where it crosses the x-axis. Yes, right.
In the back, it said that I was a 2 and 3 power.
Whoa. Say that again. On H19,
Yeah,
it said what was an inflection point?
I was a 2 and 3 power.
That's weird. I can see that though.
I see. Yeah, that's a mistake.
Okay.
That's a mistake. Matter of fact, that's something that I will spend a lot of time emphasizing to you in some later problems we do. Let's talk about why they did that, though. What happens at pi halves? Concave up on the left of pi halves, and on the right of pi halves, concave down. So at pi halves, it switches concavity. Okay, so let's be real clear about this. An inflection point is the point on the graph where it switches concavity. You can't have an inflection point if there is no point, right? So the book is a mistake. Okay? So there is a change of concavity. Now, if the question would have said, at what x values is there a change of concavity? That's a different question, right? Doesn't sound like a different question. It sounds like the same thing. Inflection point is a change of concavity, right? But it's a point. So there has to be a point for it to be an inflection point. So there are a few mistakes in the answer book, not too many though. Most of the time you can trust what the book says. But every so often there is something. And that would be a mistake. I'm glad you pointed that out. And then where does F have vertical asymptotes? We talked about that. Pi halves, 3 pi halves would be the ones. Okay? All right. So that was kind of a tricky one because, that's probably a trickier problem for the most part than what you'll have to deal with tomorrow. Aside from that C, and not that exact question, but just be prepared for that periodic, even odd, just any of these questions that you might have to stretch a little beyond just the routine on some of those things. But there'll be plenty of questions that I think are just pretty much routine as well. All right, 47 through 49. So on 47, 48, they were very, very similar kinds of questions. You had, on 47, it says you've got y equals 2 is a horizontal asymptote. Now, let's talk about this a second. A horizontal asymptote, there's a little bit of a misunderstanding on horizontal asymptotes. Horizontal asymptotes can be crossed. I could have a graph. Remember, an asymptote just means something that the graph is approaching, right? I could have a graph that does this. Okay? Isn't this graph approaching y equals 2 way out here and way out here, right? I crossed it. That's not a problem. Now, on a vertical asymptote, we'll jump ahead to 48 real quick here. 48, oops. 48, they say, is a vertical asymptote at x equals -3, okay? So you've got this situation here, and you've got a vertical asymptote over here. Now, if I drew a graph that was approaching this, but then crossed it, what would be the problem with it? Not a function. It doesn't pass the vertical line test anymore, right? So you can't cross, and plus that's where a function's undefined. That's when you get a vertical asymptote, is when the function's undefined. So you're not going to get a vertical asymptote to cross, the function's not going to cross a vertical asymptote. But on a horizontal asymptote, very well could. Okay, so this red graph could be a plausible graph for what we're talking about. So it doesn't matter that you drew this, but I think it could help you see. Okay, so 47, it says, if you did f of x plus 3, what's that do to the graph? Up 3. So if you take that red graph and shift it up 3, doesn't it make sense that y equals 5 is your new asymptote? Yeah. Okay, part B. Shift it left 1. What's going to happen? Nothing, right? It'll still be y equals 2, right? It's still going to approach 2, yes.
So is the horizontal asymptote all that's saying is that's what y can't be in the graph?
No, because y could be 2, right there.
So what is it?
Horizontal asymptote, here's what it's saying. Out at the far edges is what it's saying. Horizontal asymptote, actually that's what a vertical asymptote's saying too, is at the far edges, that's what it's approaching. So a horizontal asymptote just means the graph when it gets way out here is going to get close to 2, and when it gets way out here, it's going to get close to 2. But in between, it could hit the other ones. Now, vertical asymptote, same thing. When it gets way up here, way down here, it's approaching those things. But the reason it can't cross it is then it would fail the vertical line test. Okay? But a lot of people think that you can't cross horizontal asymptote. That's not true. You can't. Okay? All right, so the last one, C. So if we shift, now we got to do these in order, right? We start on the inside of the parentheses. So on the inside of the parentheses, we would shift left 4, right? What would that do to this?
Nothing.
It would it would shift the graph left 4, but this would still be the horizontal asymptote. Still going to be approaching 2 out at the middle. Okay? Then we would do the 3. What's the 3 do? Vertical stretch, right? On the outside, it does what you think it would do. The inside would be a shrink. But on the outside, it's a stretch of 3. Remember what a stretch does. It takes all the y values and makes them 3 times as much. So all these y values that are getting close to 2 are now what? Getting close to 6, right? So like these values here, 1.999, are now going to be 5.999. And these points up here, they're like 2.001, are now going to be 6.001, right? They're going to be 3 times as big. So I guess 2.01 will be 6.003. Doesn't matter, it's still getting very close to 6, right? So, and then we do what? What's the last thing? Up 1. So we were at 6, move everything up 1, now we're at 7. So the vertical asymptote would be y equals 7. Okay? So we go to 48. Okay, again, I love that question. You talk about what's going to be on the quiz and those kind of things. The cool thing about a question like that is it just makes you think about asymptotes, makes you think about the shifting in a different way, in a way you hadn't really thought about shifting. Okay? 48. So in this one, if you shift, so if we had a graph that was doing this, let's say, and then it maybe came up here and did this, whatever. Okay, vertical asymptote here. So if we took that graph and shifted it up 3, same vertical asymptote, doesn't change. Okay, B, we shift that left 1. Now where are we? Now the vertical asymptote would be at -4. Okay, so the x equals -4. Okay, and then we do the same thing here. We shift it left 4, so it's now going to be where? -7. If we move everything left 4, this vertical asymptote will be at x equals -7 now. We stretch everything by 3. Not going to change anything, right? These just go up faster. That'll go down faster, but it's still going to be approaching, where are we? -7. Okay, and then the last thing is shifted up 1. No change. So x equals -7 would end up being the vertical asymptote. Okay, so some things have an effect, other things would not. Okay, and then 49. This is very similar to a problem we did the other day. Okay, so Alex, you're still going to be our presenter here. So if you would put that first equation in for number 49, the x minus 3 over x squared minus 9. Yeah, I have to put the parentheses in. Okay, and any of the rest of you can put it in if you want to. Probably not going to get into this. I mean, I might have you put some functions into a calculator, but probably not going to get into a lot with the asymptotes and stuff like that. Okay, so we won't spend a great deal of time here. Okay, now hey, that's cool. Show everybody what you just did.
Oh, I always changing the attributes when you go to actions and then attributes.
Okay.
You can select it and do lots of different things.
There's
like
different.
change
You can, if you've got multiple graphs on your screen, you can change colors. You can change to dotted lines. You can make them thicker. There's a variety of things you can do. It's under attributes. For the most part, there are a few times when that's important, but most of the time it isn't too big a deal. Okay, that was in the menu under actions, and you're free to play around with those things. But if you look at what we have now, you've got just kind of a standard window there. It looks like. Okay, so we clearly have a vertical asymptote where? At -3, right? Which makes sense. If we put a -3, we can tell, I would hope, when everybody looks at a function like this, you really focus on the bottom. And you're like, oh man, 3 would be bad, right? So would -3. Now, 3 doesn't seem to be bad here, but what do we know is there? Did we talk about this on Friday? Or maybe it was Thursday? What happens if you put a 3 into this function? You get 0 divided by 0. Go to trace and type in a 3. Trace, graph trace, type in a 3. It says undefined. Oh yeah, okay, because you get 0 divided by 0. Now, later on in chapter 2, we'll learn about how 0 divided by 0 is different than, what do you get if you put a -3 in here? You get -6 divided by 0. Those two are different types of undefined. They're both undefined, but as far as a graph, they're different. One gave us a vertical asymptote at -3. 3 gives us a hole in the graph. Now again, not a big deal for tomorrow that you recognize that, but it is a domain kind of an issue, okay? So we got 2 places, this one's undefined. If we look at the second graph they gave us, the G graph, wouldn't it be this, if she graphed it, and you don't have to, but wouldn't it be the same? be the same graph except there wouldn't be a hole at 3. What would be the point? 1/6, right? If you graphed this function and you put in a 3, you would get the point 3/1/6. Okay? Now, we can look at this on Alex's graph. She's graphed them both, so we got the red and the blue. Now, we get that one thing's kind of in the way. She can grab it and move it. Go ahead and trace now. Go ahead and trace at 3. Now notice it says undefined. 3 is undefined, but see how that's in blue? I think you can hit the up arrow, I think. And then now the up arrow switched her to the red graph, the other graph she put in. Type a 3 and hit enter. And now we do get a point. 0.16 repeating, which is 1/6. Okay? So the first one, the F graph, is undefined, the blue graph. The red graph is defined there, but otherwise they're identical. Okay, so that kind of answers part A, by the way. How are F and G related? They're identical, except at 3. Yes,
So
sir.
then where it asks, like I think you talked about that too, how they're different and others.
Yes.
Like you would have to include that in your answer. that
Yeah.
they're identical except for this.
As a matter of fact, that's what I'm sorry, I misspoke. I was thinking about D. How are the graphs of F and G related? They're the same except at 3. F has a hole there, and G does not. Now,
So
yeah,
like
go
if
ahead.
that were on a quiz, we would have to include that.
Yes, you would want to say something about that. Now, it says, show that F is equal to G for all x such that x is not equal to plus or minus 3. So this is that thing, I think I was mentioning this to you guys, about how Mrs. Andreessen kind of lied to you. We all kind of lie in Algebra 2 when we do these problems. You have x minus 3 over x squared minus 9, and we tell you to simplify that. So what do? You factor the bottom, and you get x minus 3 and x plus 3, and then you cancel. Right? And then you get 1 over x plus 3. And we say that those are equal. Well, really, they're not equal. They're almost equal. They're equal all the time except at x equals 3. Okay? So at x equals 3, this one has a value, this one does not. Now, they said at plus or minus 3, and that's fine. It just means they are equal except at those two values. Now, they're actually, I guess the reason they say plus or minus, as long as x does not equal plus or minus 3, because you can't, undefined is not a number, so you can't have undefined equals undefined, I guess is why they include that. Not a big deal. But if you want to know how you would show your work on A, and this won't be on the quiz tomorrow, so don't worry about that. But if you want to know how to show that they're equal, this would be it. That would basically be it.
So, when it asks for the range of F,
Yes.
the book's answers did not include 0 or 1/6.
Okay? And that gets to the question where it was talking about horizontal asymptotes too. Notice that that's what you have here is a horizontal asymptote. It's approaching 0, but it never actually hits 0. Now, why that is? Because the only way a fraction can ever equal 0 is what? If the top is 0. A fraction can only equal 0 if the top is 0. So let's look at these two functions. Will the top ever be 0 here? No. Will the top ever be 0 here? It will,
But then
but so is the bottom, right? If you put a 3 in the top and get 0, you put a 3 in the bottom, you also get 0. 0 divided by 0 is undefined, it's not 0. So these two will never equal 0. So that's why the range doesn't include 0. And on the blue graph, it can't include 1/6 either because there's a hole there. So that is tricky. So the range would be from negative infinity up to 0, from 0 to 1/6, and from 1/6 up to infinity. That would probably be easier to just write all values except 0 and 1/6. That might be an easy way
We talked about the notation
to do it. Uh-huh.
how it said.
Is that what they said?
Well, no, it just had like U's in it.
Oh, I don't, yeah, that means, that's kind of and. So if if it said negative infinity to 0, I would just put commas there. But if you and they put U's in there. So was their answer like this? Except with U's in between? Yeah. U means union, the set, those combined together. So. Fancy orientation, not very fancy. But if you see that's what. Okay, let's see, anything about 49 horizontal asymptote, that'd be at right or 0. Vertical asymptote, we said was at NC. All right, so let's finish up regarding the quiz then real quick. To me, we've kind of said it all as far as how the quiz, things for the quiz. Some things you certainly can plan on. Obviously, the homework questions you've done, knowing the thing of a circle like we reviewed that earlier. We've talked quite a bit about this even odd periodic, showed you a variety of things. We've done a calculator one where we traced and found maximum and those kind of things. Go back over notes, go back over old homework, I suppose, if you want to. But that's kind of it for the quiz. Okay. I want to get through a little bit of trig stuff here and give you some work time on some trig review if you want to, or if you want to do some stuff, ask me some questions or do some things as far as the quiz tomorrow. So if you would pull out that packet that we did the very first day of class and turn to the last page. Okay? Because I want to take just a little bit of time here to review and just sharpen you up a little bit on the trig stuff. For some of you, I think this will go, you got it, you feel good about it, that's great. But there's probably many who are not quite as sharp on it, so I want to give you the opportunity. I do have a trig review video up on the website. It won't be important for tomorrow as far as having to know this stuff. This will not be on the quiz. Okay? But the next quiz, not really either. But then when we get into chapter 2, at that point you pretty much, these things may start showing up on assignments, and possibly when you can't use your calculator. So I have an attachment on the website. I think it's under the documents place. I have a unit circle. If you want to print that out and stick it in your notebook, it's got all the values on it going around. Pi 6, pi 4s, pi 3rds, and so forth. So that's something, you can't use it on a quiz or anything, but you can certainly use it on homework, and you can, review with it and stuff. A couple of basic things with trig, the old SOHCAHTOA stuff. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. That old right triangle stuff from geometry class. You did some of that in trig last year, I know. Then, of course, our unit circle here. If we go to 30 degrees, which is pi 6. Now, remember, first coordinate is what? First coordinate is cosine. Second coordinate is sine, and that was the thing I was saying. I think I said this to you guys the other day. I just remember because sine is y, and they rhyme, right? They have long I sounds, sine and y, sine and y. Okay? But there is a reason why that is the way it is. If you look at the right triangle in the unit circle, remember the hypotenuse is always 1. So this is the x coordinate, this is the y coordinate right here. The sides of the triangle are the x and y coordinates of it. So if you do the old SOHCAHTOA business, sine is opposite over hypotenuse, y over 1, which is y. So that's why sine is y. And cosine is the adjacent over the hypotenuse. So it's x over 1, or just x. So that's why the x coordinate is cosine and the sine coordinate is y. Okay, it's because the hypotenuse is 1. All right? So then, we just going around the circle, you have your 45 or pi force, root 2 over 2, and your 60. Okay? And then, of course, at 90, remember cosine's the first coordinate, so at pi halves, you have cosine is 0, sine is 1. Then when you get into this quadrant, all the x's are negative. So cosine is negative over in this quadrant. Okay, so the first coordinate's negative, so cosine is negative over here. And over here at pi, cosine is negative. Get down to the third quadrant, they're both negative. X and Y are both negative down here. So cosine and sine are both negative down here. And then we get the 3 pi halves. And then finally in the fourth quadrant, the x's are positive, but the sines are negative. So the y values are negative. Okay? So knowing those values is very, very important. So look at that unit circle and do it. Okay, one last thing I want to show you, then I want to work a few off that worksheet. I think this is cool. This connects the unit circle. You probably saw this last year. This connects the unit circle with our graph. So if we're going to look at the sine graph, okay, oops, yeah. So if we're going to look at the sine graph, okay, get the right one. So if we're going to get on the unit circle here and look at the sine of that point, it's going to be the y value. So it's that blue distance. This blue distance is the sine because it's the y. So over here, I'm going to graph that blue distance. So as we move this point around the unit circle, the y is getting bigger. And so the sine graph goes up. Makes sense. Not only that, but look at, as it gets up here, look at the blue line right up here. Is the blue line getting big very fast? We kind of connect this to some of the stuff we've been talking about. The blue line is not getting big very fast. Now, down here it did. Down here it grew very fast. But up here, it's not growing very fast at all. Look at this. It's leveling off. Right? And then over here, now the blue line's getting big or smaller. So the sine graph's going down. Now it's negative. So the blue graph goes negative. And now it's getting smaller and back towards 0. So that's the sine graph. Okay, as it goes around. So now let's look at cosine. Cosine is the x. So when we start, the x is big. The x is a 1. So this green distance is big. And so that's why cosine starts up high. But as we move this point around, the x gets smaller. So that's why the cosine graph goes down. And now it gets bigger again, but negative. And now it gets smaller again, still negative. And now it's getting bigger again, but positive. So the green line's getting bigger and positive, and so the cosine graph goes up. Okay, and then we can show them both. Kind of fun. There it goes. Okay, so the values on the unit circle connected to, the graphs of sine and cosine at various points along the way. Okay, all right, enough of that. All right. So what I would like to do is take a look at this worksheet that you had, and all right, let's go through a couple of these. All right, so I'd like to do number 3 with you real quick here, and I know hopefully you had a lot of these done, but maybe you ran into some difficulty with some of these. And let me show you how the unit circle comes into play. Now again, not for tomorrow. Not going to have to do this, but give you a chance to see what you're going to have to be able to do. And between now and we get to chapter 2, when you're pretty much going to have to be able to do these, you know what you need to work on. Okay, if you want to come in and get some help with me, have me go through it with you a little slower, a little more in depth. I'd be glad to do that. Okay, we get to this point, we get cosine by itself. We got to ask ourselves, where's that at? Well, we got to think of the unit circle. And where is the cosine, which is the x, where does it equal root 3 over 2? Well, it's right here at this point. This is the point root 3 over 2, 1/2. And that's when, oh, it's negative. Never mind. It would be over here, wouldn't it? Be over here. Negative root 3 over 2, 1/2. It'd be that point. What other quadrant would it be in? Be down here, right? At the point negative root 3 over 2, negative 1/2. Now what angle is this? Well, okay, but the reference angle would be, yeah, I always like to do reference angle, but it's pi 6, right? It's pi 6 because this one here is pi 6, the one in between is pi 4, and the one that up closer to the vertical axis is pi 3. So this one's pi 6. Now, what I like to do, what helps me, and I know I've talked to people, kind of helps them, this is pi. Think of that as 6 pi 6, or 4 pi 4s, or 3 pi 3rds, depending on which one you're doing. In this case, we're doing pi 6, so think of it as 6 pi 6. So you're 1 pi 6 short of that, that'd be 5 pi 6. And here your 1 pi 6 past it, so that's 7 pi 6. So your answer here is going to be 5 pi 6 and 7 pi 6. We're only supposed to go from 0 to 2 pi for 1 time around. Okay, so that's a fairly just kind of basic one where you get the cosine by itself, you got to know the unit circle, and you get the right quadrants, and you give the answer. Okay, then you get to some where you have a little more algebra. Okay, for example, number 6 here. Number 6, what should you do here? You'd be tempted to factor out a cosine, but that would actually be bad. You got to subtract 3. Yeah, you can't, you really never want to factor unless you can cancel something, unless you have set it equal to 0 first. Factoring doesn't really do you much good unless you've set it equal to 0. Now we can factor, except it would be a FOIL kind of thing. So we have cosine x to get our cosine squared. And then to get 3, we'd have 3 and 1. We'd want 3 to be positive, 1 to be negative. So now you set each of those equal to 0. All right? I apologize for, I know I'm going kind of fast, but like I said, I'm just kind of trying to show you what things we need to be able to do, what do I need to work on before we get into chapter 2 and allow you to do it. So now we get cosine x equals negative 3. We get cosine x equals 1. Again, stop me at any point if there's something you want to ask me about too. All right, what about cosine x equals negative 3? That is a lot. That will never have I like that. That will never happen. Cosine can only have outputs from negative 1 to 1. So cosine x can never equal negative 3, so forget that. Cosine x equals 1, so now we go back to the unit circle. Cosine is the x. Where does that equal 1? Only right there. So that would be at x equals 0 or 2 pi, but I think they told us not to include 2 pi in the direction. So just 0. So an angle of 0 would be the only one right there. Okay? All right, and then the last one I wanted to do is number 9. Okay? Now, did anybody, and I know you might have saw my work on this one, and maybe not, and I don't remember how I did it. Yeah, I did a substitution. I did a substitution thing, okay? Now, some of the other, I saw several different things from the other class, so let me see if this applied to any of you guys. Several of them in the other class did this. They added the cosine squared over. Then they divided by cosine squared. Okay, I'm getting tired right now, so I'm going to be lazy. What is cosine squared over cosine squared? Tangent squared equals 1. Then they did the square root. Where does tangent equal plus or minus 1? It's root 2 over 2 over root 2 over 2. In other words, it's when sine and cosine are the same, right? Because tangent sine over cosine. So when will a fraction be 1? It's when the top and bottom are the same. Well, sine and cosine are the same at pi fourths, root 2 over 2. Now it could be plus or minus 1, so they could be opposites. One could be positive, one could be negative. So that gives us all 4 quadrants. So it's going to be pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. Now, there is a bad thing they did here, though, that actually doesn't turn out to hurt them here, but anytime you divide by an x, you are possibly losing some solutions. You're losing any solutions where this is 0. Now, where is cosine 0? Pi halves, 3 pi halves. Turns out that those are not solutions to this anyway. So, it turns out you're okay. But let me just show you what I mean by that, why you have to be careful dividing by an x. If I gave you this problem right here, most of you, I hope, would think of doing what? You'd factor out an x, right? And you would get for your solutions, right? However, if you did what this person in the other class did, On this problem, you would add the 3x over to the other side. You would divide both sides by x. You would get x equals, right? You would lose the solution x equals 0. And that's because you divided it out of it. So anytime you divide by an x, you lose the solution, the possible solution where that thing was 0. So you have to remember to go back and double check and see if it would work. So you do bottom line is anytime you have an equation you divide by an x, you ought to be kind of nervous about it. Okay? But in this case, it works out okay. I mean, like you ought to get little goosebumps when you do it. I mean, it should be like, ooh, something weird's happening. But anyway. All right. The other thing that I saw people do was this. They factored it. Sine plus cosine, and then sine minus cosine. Right? Doesn't that make sense for this? Difference of squares. And then they set each of those equal to 0, and what you end up with is sine equals negative cosine, and sine equals cosine. Well, that's still pi fourths, right? Where does sine equal cosine? At pi fourths, and in the third quadrant, when they're both negative, at 5 pi fourths. And then where is sine the opposite of cosine? Well, that'd be quadrants 2 and 4. So you end up with those same 4 answers. Okay, so that would be okay, but it's harder for people to see. And then the one that most of you did is, remember, sine squared plus cosine squared equals 1, right? So sine squared is the same as 1 minus cosine squared. So I could substitute that right there. So in place of the sine squared, I could put 1 minus cosine squared x minus cosine squared x equals 0. So I could substitute to make those be the same. Now I get 1 minus 2 cosine squared x. Subtract the 1. Divide by the negative 2. Gives me 1/2. Square root both sides. What is the, it'd be plus or minus, what's the square root of 1/2? Root 2 over 2. Because if you square root 1/2, you get this, which is 1 over square root of 2. And then you rationalize that, you get root 2 over 2. So where does cosine equal plus or minus root 2 over 2? Well, sure enough, it's those 4 places. Pi fourths, 3 pi fourths, 5 pi. Okay, so 3 different ways that we could have got it. But that's a tough one, a little tougher. You got some algebra there, you got a little substitution, things like that. We won't get into those that much, but you will run into some of these basic ones with the unit circle as we get into chapter 2. So what I've got for you here the rest of the time, last 20 minutes or so, you can decide. You can work on just quiz review if you want to go back over your homework. You want to ask me some questions that you might have over that. I've got a little worksheet here with some trig equations on it that would be good practice. We're not going to hand it in or anything, but it's just something you can do for some trig practice. This would be a pretty good time to do it. We probably won't do much more of it before chapter 2 when we're going to need it. So there is an appendix in the book where we will do a little more trig stuff too, I think, after the quiz tomorrow. But those are the things you can work on the rest of today.
Mr. Clark,
Yes, ma'am.
it's raining and replenishing the aquifer.
See, that's cool. That's some calc biology interdisciplinary stuff going on there. I love it. I love it. Yes, sir.
So I did all this stuff. I got 1/2, and it comes in as a -1/4.
Oh, yeah.
So it ended up.
You'd have to use a calculator for that. Yeah, yeah. So, right.
Well, I know how I do it, I just don't.
So is that your question? Like,
Like,
is there any way you should know?
Is there a better
No.
answer than
No.
what I did?
No,
Or?
there's no way you should know 12 plus 4 is. No, that's just you know, you get the right quadrants, which it looks like you did. That'd be the first knowing Oh, that'd be the second. No, that's second. That's second, third part. Yeah, which is where it would be. Yeah, no, there's no middle. Okay.
The game's at 5.
Nice.
So we were appointed to 1:50
Oh.
Wednesdays.
150 on Wednesday. Oh,
Yeah. I can come in and do it. But I think if you get
come
her
in
in,
and do what?
cover this for last few months. Oh.
All right.
If it would have been 5:30, I could have done it, because the appointment was actually at 4:10. But I thought, I don't want her to miss that last game.
So you're able to sneak her in Wednesday. This
Wednesday at 1:50. Is that okay?
Yeah, we can.
Now, that's also the day where we're supposed to meet with those people. But you can get back for the second half of that, I would think.
They could have done a third one in the 12 o'clock. Yes.
11:30.
You know, but there's probably an episode of Johnny Bravo. There are episodes of Johnny Bravo where he's a woman. Are you still recording?
Oh, yeah.
I love how that's going to be at the end of your recording now.